Fluid flows have two classifications: the external, which is the flow of an unbounded fluid over a surface, and internal, if the fluid is completely bounded by a surface. Liquid or gas flow through pipes or ducts is commonly used in heating and cooling applications and fluid distribution networks. Friction is directly related to the pressure drop and head loss during flow through pipes and ducts. The pressure drop is then used to determine the pumping power requirement. In fluid flow, it is convenient to work with an average velocity, which remains constant in incompressible flow when the cross-sectional area of the pipe is constant. The value of the average velocity at some streamwise cross-section is determined by the requirement that the conservation of mass principle be satisfied. The average velocity for incompressible flow in a circular pipe of radius can be expressed as shown. An inspection of flow in a pipe reveals that the fluid flow is streamlined at low velocities, but turns chaotic as the velocity is increased above a critical value. Laminar flow. The flow of a fluid when each particle of the fluid follows a smooth path and is characterized by a highly ordered motion. Turbulent flow. An irregular flow that is characterized by velocity fluctuations and highly disordered motion. Transitional flow. It is the mixture of the two flows, which occurs over some region in which the flow fluctuates between laminar and turbulent flows before it becomes fully turbulent.
Reynolds number. It is defined as the ratio of inertial forces to viscous forces. Now, what does Reynolds number used for? Reynolds number help us determine whether the fluid flow pattern is laminar or turbulent. The number has no unit or dimensionless. 2300 is the reference number at which, if the Reynolds number is less than or approximately 2300, fluid regime is laminar flow. If the Reynolds number is in between 2300 and 4000, the fluid flow is transitional, which means laminar and turbulent flow switches simultaneously. Then, if Reynolds number is greater than 4000, flow pattern is turbulent.
When the fluid enters a pipe, the particles in contact with the boundary will slow down according to the no-slip condition. The region of the flow in which the effects of the viscous shearing forces are felt is called the velocity boundary layer. The hypothetical boundary surface divides the flow into two regions: the boundary layer region, in which the viscous effects and the velocity changes are significant, and the irrotational flow region, in which the frictional effects are negligible and the velocity remains essentially constant in the radial direction. As can be seen in the figure, the thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center and fills the entire pipe. The region from the duct inlet to the point at which the boundary layer merges at the center line is called the hydrodynamic entrance region, and the length of this region is called the entrance length. Flow in the entrance region is called developing flow, since this is the region where the velocity profile develops. The region beyond the entrance region, in which the velocity profile is fully developed and remains unchanged, is called the fully developed region.
So intralets. So the hydrodynamic intralet is usually taken to be the distance from the pipe entrance toward the wall stress. So and thus the friction factor. reaches within about 2% of the fully developed value. So L sub H laminar all over D is approximately equal to 0.05 RE. So that is the hydrodynamic interlength for the laminar flow. And then LH turbulent all over D is equals to 1.359 RE raised to the power of 1/4. That is for hydrodynamic interlength for the turbulent flow. And then L sub H turbulent all over D approximately equals to 10. So hydrodynamic interlength for turbulent and approximation. Laminar flow in pipes. So we consider steady laminar incompressible flow of a fluid with constant properties in a fully developed region of a straight circular pipe. So in fully developed laminar flow, each fluid particle moves at a constant axial velocity along a streamline, and the velocity profile remain unchanged in the flow direction. There is no motion in the radial direction, and thus the velocity component in the direction normal to the pipe axis is everywhere zero. So there is no acceleration since the flow is steady and fully developed now. As you can see the diagram or the figure now. So this is a freedom body diagram of a ring-shaped differential fluid element of radius r, thickness dr, and length dx oriented coaxially with horizontal pipe in a fully developed laminar flow. So as you can see this So this is a free body diagram of a fluid disk element of radius r and length dx is fully developed laminar flow in a horizontal pipe. So for the boundary condition, so AU all over AR is equals to 0 at R is 0. And then U is 0 at R is equals to capital letter R. That is for the boundary condition. And then you can use this equation for the average velocity. And then for the velocity profile, you can use this. And then for the maximum velocity at center line, we can use this. So all in all, that's all. I hope you learned. Thank you.
Pressure drop and head loss. Pressure drop is the difference in total pressure between 2 points in a fluid carrying network. There are two types of pressure losses, and these are major losses and minor losses. Major losses are caused by friction or viscosity and major leakage, while minor losses are caused by sudden contraction and enlargement of pipes, pipe entry and exit, bend in pipes, junction of pipes, and minor leakage. Pressure drop in laminar flow is expressed with this formula. Delta P is equal to P1 minus P2, which is equal to 8 eta L V average over R squared, which is equal to delta P is equal to 32 eta L V average over D squared, where eta is equal to the dynamic viscosity, L is equal to the length of pipe, R is the radius of pipe, D is the diameter of pipe, and V average is the average velocity. The pressure loss formula is expressed with this equation, where density times average velocity squared over 2 is equal to the dynamic pressure, and F is the Darcy friction factor, which is equal to 8dW over density times average velocity squared. So why is studying pressure drop important? Pressure drop is a significant physical and monetary contemplation when working with sub-atmospheric and vacuum applications. By knowing how much pressure drop each part causes, you can assess how much pressure is required to run your cycle. The lower the overall pressure drop of the system, the lesser the gas usage in order to run it, which saves resources and money. Head loss. Head loss is a measure of the reduction in the total head of the fluid as it moves through a fluid system. It is caused by viscosity and is directly related to the wall shear stress. Head loss, or HL, represents the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in the pipe. head loss has a formula of HL is equal to delta P L over density times G, which is equal to F times L over D times V average squared over 2G, where F is equal to the friction factor, L is the length of pipe, D is the diameter of pipe, and V average is the average velocity.
And now let's proceed to the laminar flow in non-circular fluid, because not all the conduits used to transport fluids are circular. So for example, there are ducts that used for heating, ventilation, and air conditioning in buildings that have a rectangular cross-section. Remember, in the circular pipe, if the Reynolds number is equal or less than 2,300, then the fluid is in laminar flow. So if the flow is fully developed and laminar, the friction factor will be constant over the Reynolds number. So the Reynolds number in a non-circular fluid uses the hydraulic diameter, and the constant is related to the shape of the duct. So this hydraulic diameter is defined as 4 times the cross-sectional area of the flow divided by the wetted perimeter. So in this illustration, the wetted perimeter is the length of the wall that is exposed to the fluid. But since the rectangle is completely shaded, this letter L will be the entire perimeter of the duct. And the color orange shaded region A is the entire duct cross-sectional area. So observe in this table, in which the friction factor oscillations are given for fully developed laminar flow in pipes of the various sections. So in the circular pipes or the ducts, the constant of the friction factor is 64, while the non-circular ducts such as the rectangle, ellipse, and the isosceles triangle, the constant of that friction factor will be based on the shape of the given duct. So that's how the laminar flow in non-circular fluid.
Moody chart, or also known as Moody diagram, is a graph in a non-dimensional form that relates the Darcy Weisbach friction factor Fb and Reynolds number Re and surface roughness or fully developed flow in circular pipe. It can be used to predict pressure drop or flow rate down such a pipe.
Yo, what's up everyone? This is Justin, and let's learn about turbulent flow and minor losses. In reality, the flow of a fluid sets up inside a pipe, such as a liquid water flowing inside a pipe, is defined as turbulent. It is because of the normal friction and the geometry of the pipe and the fitting of the pipe. And thus, we can also observe eddies or the swirling effect in a turbulent flow, and it affects the flow of fluid inside our system. And because of the presence of eddies or the turbulent flow, the flow of fluid that we desire is decreased. And in order to deal with such turbulent occasions, we must learn about how to deal with it and how to understand turbulent flows. But it is quite complex and challenging. But as engineers, we will learn it and we will achieve our goals. Now let's talk about minor losses. Minor losses are caused by the fitting, elbow, curves, and edges in a piping system, such as in the image. Because aside from a straight pipe, the fluid flow is straight or direct, but in such systems with edges, elbows, etc., the fluid flow is affected. So we must learn about minor losses in order to achieve our goal. Now, in equation forms, the minor losses, or defined as the letter K, is defined by this equation. And if you want to find the head loss and we are given the K value, we can use this equation. For the total head loss, it is defined by this equation. And for the total head loss, where the D is constant, we can use this. Now, for different types of fittings in pipe, there are also different values for K, such as in the image here. We can see that they are different from each other, and also they have different K values, such as in the first one, we can see that the K is 0.8, and the second, which is sharp edged, is the K is 0.50, and so on and so forth, just like what we can see here in the images. And that's it. I hope you learned. Thank you.